Hi everyone, I'm Bailu from Microsoft Research. Today I'll be talking about DSB, a decision support benchmark for workload-driven and traditional database systems. This is joint work with Surajit, Johannes, and Vivek. Why do we need a new benchmark? The industry standard TPC-DS benchmark is widely used for evaluating database systems on decision support workloads. It models the data warehouse of a retail product supplier with realistic database schema. It imposes realistic data distribution from sensor data, and the query templates simulate the meaningful queries of business semantics. The database is scalable, and the queries are parameterized. With all these merits, why do we need yet another decision support benchmark? After a decade since the publication of the TPC-DS benchmark, we have observed several new trends in decision support workloads. The database content now has more complex data distribution. There is not only skews on individual columns, but also correlations between columns within the same table, and correlations of columns across multiple tables after joining them together. Also, we have observed more query patterns. In addition to the star or snowflake queries with fact tables and dimension tables, we also see non-equi joins and joins with non-primary key foreign keys. Finally, instead of reporting aggregates over a large amount of data in the database, with the popularity of data science, there are more fine-grained data slicing in the queries, with more tables joined together and more predicate filters. In addition to the new trends in the workloads, we have also observed the surge of workload-driven database systems. These workload-driven database systems re-architect some database components by leveraging the workload and the execution feedback of the workload, especially with machine learning techniques. Such database systems demand new requirements to our benchmark to better assess their capabilities and performance trade-offs. For example, these workload-driven database systems can require a training workload, which is different from or better distinct from the workload used for the actual evaluation. This requires the benchmark to be capable of generating a sufficient number of distinct query instances. Surprisingly, the TPC-DS benchmark, which is considered as a complex decision support benchmark, does not fulfill this requirement. In fact, for some query templates, the number of distinct query instances that can be generated is as small as 5. Second, one important aspect of our workload-driven database systems lies in its capability of adapting to the change in the workloads. This requires evaluating the system with dynamic workloads, including changing query distributions and shifting of the parameter distributions in the queries. Finally, these workload-driven database systems can have different performance trade-offs with traditional database architecture, including the overhead from training and inference before and during query execution. The performance metrics of the benchmark should expose such trade-offs to compare database systems of different designs fairly. To fulfill these gaps, we think it is time to design the next generation of decision support workloads. We propose DSB, a decision support benchmark that is especially designed for evaluating both workload-driven and traditional database systems. The DSB benchmark is adapted from the TPC-DS benchmark with enhancement in more complex data distributions and new query templates. The benchmark is capable of generating a large number of distinct query instances and dynamic workloads. Given that the evaluation setups of recent workload-driven database systems diverge because of the lack of a standard, we also provide guidelines for evaluating methodology and metrics to report to help compare traditional and workload-driven database systems in a fair manner. Let's first take a look at the highlight of the DSB benchmark in data generation and query generation. We introduce more skews and correlations into the data generation to reflect the complex data distribution in the real world. For data in a single column, we introduce skewed exponential distribution for categorical values, The distribution is also introduced to columns with numerical values after bucketizing the domain. In real data, there can also be data correlation between columns in the same table. For example, it's very likely that the items in the same or similar categories are overseen by the same manager. This leads to data correlation between the item and manager columns in the item table. We introduce multi-dimensional exponential distribution to capture such correlation. Furthermore, some data correlation spans across multiple tables. For example, it's likely that the people from California buy more shorts than people from Alaska. Such data correlation, however, can only be discovered after joining multiple tables with related information. To simulate such complex data correlation, we also introduce exponential distribution on the join result of multiple tables. In addition to more complex data distribution, we also enhance the query templates with meaningful and more complex query patterns, including non-equijoin, self-joins, and cyclic joins. For example, the new query templates 100 tries to find two products that are frequently sold together. This involves non-equijoins between a dimension table and a self-join between a fact table. Similarly, the new query template 102 tries to understand the customer behavior for those who first buy an item from the store and then buy it again from the web. This requires a non-equijoin on a dimension table and a cyclic join between a number of fact and dimension tables. Previously, the reporting is often aggregated over a large amount of the data in the database, such as query the total number of items sold in the first quarter. With the increasing popularity of exploratory data science, people are trying to get more insights from the data with fine-grained data slicing. For example, instead of getting a high-level overview of the sales data, the business analyst also tries to find patterns for the sales data by different item categories and customer demographics. We enhance the query generation with fine-grained data slicing by drawing more related tables with more predicate filters. Combining this with complex data distribution, these queries impose additional challenges in cardinality estimates and query optimization. As a side effect, this data slicing also helps generate more distinct query instances, which is often required by the evaluation of workload-driven database systems. Finally, to fully assess the capability of adaptive database systems, the DSB benchmark also provides flexibility in generating a variety of workloads. The benchmark can generate a sequence of workloads. Each workload is configurable in terms of the query templates used and the number of query instances per template. The distribution of the query parameters is also configurable. Currently, the DSB benchmark supports two options to generate query parameters. The first one is uniform distribution. The second one is Gaussian distribution. The center of the parameter and the variance of the parameter distribution is also configurable. One important aspect of the DSB benchmark is the evaluation guideline provided. Over the past few years, together with the various efforts on redesigning the database components with workload-driven techniques, unfortunately, we find the evaluation setups diverge in these efforts. This is partly because of the lack of standards in comparing performance trade-offs between databases of different architectures. Here, we provide a guideline to fairly compare traditional and workload-driven database systems. Since the DSB benchmark provides a variety of ways to generate query workloads, and the workload can be critical for the performance of the workload-driven database systems, the evaluation should report how exactly the training and test query instances are generated and how much overlap is there between the two. To unify the workflow between the traditional and workload-driven database systems, we separate the evaluation into preparation and test stage. The preparation stage can be used for preparing the database for running the workload. This includes creating statistics in traditional database systems, as well as collecting execution feedback and training the model for workload-driven database systems. The time and resource consumption in this stage should be reported. The query performance is measured in the test stage. The metric can be the average CPU time or elapsed time of the end-to-end query execution. This includes overheads for query optimization, inference, and adapting to the workload if applicable. Now we come to evaluation. Let's first look at the comparison between the DSB and TPC-DS benchmark. At a high level, the DSB benchmark has a higher number of joins on average. On top of that, the DSB benchmark also provides a set of SPJ-only query templates derived from the benchmark. This makes it more convenient to evaluate techniques that mainly focus on join ordering. We also compare the complexity of the query templates in the DSB and the TPC-DS benchmark. We measure the time spent on query optimization as an approximation to its complexity for the queries in the two benchmarks. We observe that the average normalized query optimization time on the DSB benchmark is close to 3 times compared to the TPC-DS benchmark on both Microsoft SQL Server 2019 and Postgres 13. This shows that the DSB benchmark is considered a more difficult benchmark for the query optimizer in both database systems. We analyze the complexity in the query optimization and compare the difficulty of cardinality estimation for queries in the two benchmarks. We calculate the Q errors for the cardinality of group by queries with respect to independence assumption. Here, we vary the complexity of the group by queries from a single table to the join result of multiple tables. As we see here, the Q errors of the cardinality estimation in TPC-DS database is more or less close to 1. This means the columns in the TPC-DS database are more or less independent. In contrast, the Q errors can be much higher in the DSB database for the same group by expression. This shows that the DSB database has a significantly higher degree of data correlations between the columns and thus more complicated cardinality estimation. We evaluate the room of improvement in plan quantity for DSB benchmark. We compare the query performance of the original query plan for Microsoft SQL Server 2019 and the best plan we managed to get by tuning the query. On average, we observe that the best plans have 31% less elapsed time compared to the original query plans. 25% of the query instances see more than 20% of the improvement, and 10% of the query instances see more than 2.2 times speedup. This shows that there is sufficient room of improvement in query performance for DSB benchmark even in a mature commercial database system. Finally, we illustrate how to use the benchmark with a case study, where we evaluate a traditional database system and a database system with machine-learning enhanced cardinality estimators. For the time limit, I'll skip all the details of the case study, and I just want to highlight how we follow the evaluation guidelines to perform the experiment and report the metrics. We report how the training query workload is generated, including the overlap between the training and test workloads. We also report the overhead spent on the preparation stage. For the query performance, we report the average time and CPU time as well as their distribution. More details of the case study can be found in our paper. To conclude, we propose DSB, a new decision support benchmark for evaluating both traditional and workload-driven database systems. The DSB benchmark provides complex data distributions, challenging query templates, dynamic workloads, and an evaluation guideline to expose and assess different performance aspects. The DSB benchmark is open sourced on GitHub, and I'm happy to take any question now.